Here on YouTube, there are still people that have problems with the double-slit experiment. Formulate the standard description out loud and they become apparent immediately. When shooting an electron out of an electron gun, it is a particle, while on its way towards and away from the screen with the two slits, it is a wave, and when reaching the photographic plate on the other side, it is a particle again. And nobody says anything at all about how all this is happening. My doubts stem from earlier in the story, when being told that the wave function itself has no meaning, but when squared, it magically becomes a probability density, and that the electron was not a point particle, but a probability cloud. That seemed not in any way possible to rhyme with the discreteness of the states shown in the atomic spectra. Thus started a long road of attempts to make sense of all this, ignoring all the calls that it couldn't be done, applying some old-fashioned recipes, one of which is mentioned here by Maxwell, to study the basics of the subject, or to be more precise, to study the ones that had done work on the basics of the subject, and chose de Broglie, Schrödinger and Dirac because they used the old-fashioned and practically imaginable concept of oscillations for their discoveries. Here, as an announcement, teaser and preparation of the mind for what follows, the first and briefest kind of report on the findings. It turned out that de Broglie had not used one, but two oscillations in order to find his wavelength relation, one of which propagates with infinite velocity, so that for a particle at rest, his wavelength is infinite too. The second source of basic quantum mechanical knowledge, Schrödinger, used de Broglie's wave function and wavelength relation and turned out not one, but two differential equations for de Broglie's wave functions. The first one, that describes de Broglie's original oscillation, is the one known as the Klein-Gordon equation. The second one, carrying his name, turns out to be the one for amplitudes of the first one, is valid only for low velocities, and is also called the fundamental equation of quantum mechanics, but isn't. The third source, Dirac, took the first Schrödinger equation, which has deficiencies, and repaired these deficiencies. In order to do this, he had to increase the number of components of the oscillation from 1 to 4, and got the equation that indeed is the fundamental equation of quantum mechanics. To this recipe of more or less known things, there are added two other ingredients, the first being a new way to describe the relation between the differential equations, using their wave functions, which come with illustrations like the one shown. This is a central part of the story, and is a major part of the solution to the wave-particle problem. The other thing is new only in this context, which is the problem of when a heap of sand turns into a finite collection of grains, a situation sketched in a form suitable for physics by David Bohm. In quantum mechanics, it is called the measurement problem. And if you follow Niels Bohr and the Copenhagen interpretation, one should always use heaps of sand, as in the left part of the illustration. The clue to both the quantum problems and their solution is the realization that if you try to measure the state of a microscopic particle, you do that with the help of other microscopic particles. Albeit a lot of them, but that's of later worry. And that is the first step in what is the ultimate goal of this exercise as a whole, to make a mechanism out of a formalism, done with the help of drawings like the one shown, of which many will follow, in 6 episodes starting with a full introduction. Whether it succeeds and delivers anything useful is for you to decide. See you soon, hopefully.